Hello everybody, welcome into another lesson. So today we are going to talk about the squeeze theorem, also called the sandwich theorem. And I'll explain what you see on your screen in just a second, but the squeeze theorem, also known as the sandwich theorem, is actually a way of dealing with more complicated limits. So let's say you have a function f of x, and then you have a function h of x, and g of x is between those two functions. The squeeze theorem in short says if the limit as x approaches some number of f of x equals L, or some number for the limit, and then the limit as x approaches a at the same value of h of x equals the same value that it equaled for f of x, and g of x is between f of x and h of x, then the limit as x approaches a of that g of x equals L. So that means if g of x is between the two other functions, f of x and h of x, then if you have that f of x and h of x have the exact same limit, they're equal to each other as x approaches the same number, then g of x will also have the same limit as x approaches that number. Now, that graphic on the screen that you see illustrates why this is called the squeeze or the sandwich theorem, because you have one function squeezed or sandwiched between two others. So let's talk about what you have here. For the first function in red, so let me actually write these in their respective colors. In red, you have f of x is equal to x squared. So you're given f of x equals x squared in red. And then, let's see, in blue, what do you have for blue? You have g of x in the blue is equal to x squared sine of pi divided by x. And then, you know what? Let's get a green marker. I think a green one could help because the third curve's in green. So bear with me while I find a good green color. You know what? I think that's a good green color. Let's use that. Alright. And then in the green, we have h of x is equal to negative x squared. So you have, at this time, you have then in the red color on your screen, that red curve is the classic f of x equals x squared. G of x equals x squared sine of pi over x. That's what's in the blue. And then in the green, you have f of x, h of x rather, equals negative x squared. If you look on your screen, that curve in the blue, that trig function, is sandwiched between your two parabolas. It's squeezed between them. It's sandwiched between them, thus showing why we use the name the sandwich theorem or the squeeze theorem. And in this case, so let me write down what we have here. We have shown by this graph that f of x is less than or equal to g of x, which is less than or equal to h of x. So in other words, we have that g of x function, this trig function, is sandwiched between the two parabolic functions. Now, how are we going to solve something like this? In this case, we want to take the limit, we want to find the limit as x approaches 0 of g of x. We're going to take the limit as x approaches 0 of g of x. How are we going to handle that? Well, I'll leave these original functions up here. So what you want to do first, if you want to deal with g of x, ignore this x squared, because this usually occurs largely with trig functions. It doesn't always occur with trig functions, but largely you're going to use the squeeze theorem with some form of a trig function. So let's go ahead and dive into this here. So you have, let's pretend that g of x doesn't have the x squared. Let's just pretend we're dealing with sine of pi over x. So we're going to take the sine of pi over x. Now, you have the sine of pi over x, so what is the range of the sine function? In other words, what outputs do you get? What is your range? Doesn't sine go from -1 to 1? It does go from -1 to 1. How are you going to write that? You're actually going to then write that -1 is less than or equal to the sine of pi over x, which is less than or equal to +1. So you're dealing only with the trig component. Now, if you multiply that sine of pi over x by x squared, you'll get your g of x, but what you do to one part of this, you have to do to all parts of the inequality. So, of course, in the middle, you would end up getting x squared sine of pi over x. Now, if you multiply to the left side of the inequality, take -1, multiply it by x squared, you would end up getting the negative of x squared. And then if you multiply that 1 by x squared, you would end up getting x squared. So now you have that negative x squared is less than or equal to x squared sine of pi over x, which is less than or equal to x squared. So actually, yes, with the graph now, we see how this middle function is sandwiched between the two other ones. So what does that mean? What does that mean exactly? Let me write in blue ink here. So once you've got it worked out where you have the middle function and you multiply the other two sides of the inequality based on your range of the sine function by x squared, next thing you want to do is take the limit of each of these functions. So we're going to take the limit as x approaches 0 of the left side of the inequality, in this case of negative x squared, set that less than or equal to the limit as x approaches 0 of x squared sine of pi over x, less than or equal to the limit as x approaches 0 of that positive x squared. So now we've got the limit of each of these pieces. So let's deal with the left and right hand side. The left side is going to be the limit as x approaches 0 of negative x squared. We can just use direct substitution. We can get 0 less than or equal to the limit as x approaches 0 of x squared sine of pi over x, less than or equal to the limit as x approaches 0 of x squared, which we can use direct substitution for and also get 0. Well, hang on a minute here. If you have 0 less than or equal to this middle piece, which is also less than or equal to 0, the only logical conclusion we can come up with then is that this middle piece, as the limit approaches 0, is also 0 itself. So by the squeeze theorem, we could say that the limit as x approaches 0 of this x squared sine of pi over x equals 0. We can say that by the squeeze theorem. And the squeeze theorem is very nice for dealing with complicated trig functions with an extra factor being multiplied by it to find the limit. That extra factor of x squared is often called a damping factor. If you have a trig function and it's multiplied by anything else besides what you have the normal trig function of, that's called a damping factor. So these are great for finding the limits of damped trig functions. And I got more of these. I got a couple more. This isn't going to be a super long lesson. Let's see, let's do another one here. So, I think we could take away the graphing now. So let me adjust these windows here. 1 second, please. Bear with me. I am going to dismiss that. And then let me adjust my video window so I can see what the heck I'm actually doing here. There we go. Alright, now I can actually see what I'm doing in the full window. So let's see here. Let's take the limit. What if you had something like the limit as x approaches 0 of... I had it here. There we go. Of this function, the square root of x cubed plus x squared times the sine of pi over x. So we have a very similar function. We want to find the limit as x approaches 0 of this function here, the square root of x cubed plus x squared, that whole quantity times the sine of pi over x. Well, this is a perfect example of how to apply the squeeze theorem, because you're going to think that if you take pi over 0, the limit's not going to exist there, right? The squeeze theorem is a very good thing to use for this. So the first thing you want to do, just deal only with the sine of pi over x. Just deal with your trig function. So we're going to take the sine of pi over x. Again, now this is where the range of the function comes in. Whatever values of x I put in, the lowest value I could get is -1. So -1 will be less than or equal to that sine of pi over x. Then the greatest value I could hope to get is +1, which means then that the sine of pi over x will be less than or equal to 1. So we've set it up now with the range of possible values we could get for sine of pi over x. Now, notice the function we're taking the limit of here is also multiplied by that square root of x cubed plus x squared, which means we want to multiply the middle piece by said function, and in turn we're going to have to multiply all three pieces by that square root function. So this is going to become, if we multiply all three pieces, we'll end up getting negative of the square root of x cubed plus x squared is less than or equal to the square root of x cubed plus x squared times the sine of pi over x, which is less than or equal to the square root of x cubed plus x squared. So now we have all three pieces here that we've multiplied by the square root of x cubed plus x squared. At this time, we can proceed to take the limit of each of these pieces. So let's take the limit as x approaches 0 of this left side of the inequality of that negative of x cubed plus x squared less than or equal to the limit as x approaches 0 of this x cubed plus x squared times the sine of pi over x, which would end up being less than or equal to the limit as x approaches 0 of this square root of x cubed plus x squared. Well, we don't have to deal with the middle piece right away. Let's just deal with the left and right piece of these inequalities. So let's deal with the limit as x approaches 0 of this negative of the square root of x cubed plus x squared. We can plainly see we can use direct substitution, which would just end up giving you 0. If you substitute 0 in, that would be less than or equal to the limit as x approaches 0 of the square root of x cubed plus x squared times the sine of pi over x, which would be less than or equal to, for the right piece here, we take the limit as x approaches 0 of x cubed plus x squared. We can use direct substitution and get 0. Well, if 0 is less than or equal to the limit of this function as x approaches 0, and that's also less than or equal to 0, the only thing left to say then is the limit of this middle function as x approaches 0, the limit as x approaches 0 of x cubed plus x squared times the sine of pi over x has to equal 0. That would be the only logical conclusion by the squeeze theorem or the sandwich theorem. You're going to hear those used interchangeably. It depends what textbook you have. It depends on your professor. But the squeeze theorem or the sandwich theorem mean the same thing. All right. I have 1 to 2 more. Let's see what we got here. Here you go. We're going to take the limit as x approaches 0 of x squared cosine of 20 pi x. So let's take the limit as x approaches 0 of x squared cosine of 20 pi x. So we have another damped trig function. Damped. I want to say that. I don't want it to sound like I'm cussing. It's damped. D-A-M-P-E-D. So I'm not cussing, I promise you. But first thing we want to do again, ignore this x squared. Just deal with the cosine of 20 pi x. So take that cosine of that 20 pi x. Now, what is the lowest value we could get for this function? The lowest value we could get is -1, so -1 will be less than or equal to this function. And then the greatest value we could hope to get is +1, so that's going to be less than or equal to +1. Now, we notice we have an x squared piece on this function, so let's go ahead and multiply everything by x squared. You'll end up with the negative of x squared is less than or equal to x squared cosine of 20 pi x, which is less than or equal to x squared. Now we have this set up where you have the full function in the middle piece. Now all that's left to do is take the limit of each of these three pieces as x approaches 0. So the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of that x squared cosine of 20 pi x, which is less than or equal to the limit as x approaches 0 of x squared. Well, let's first deal with the left and right side. The limit as x approaches 0 of negative x squared, by direct substitution, we can say 0. That's less than or equal to the limit as x approaches 0 of this x squared cosine of 20 pi x, which is less than or equal to the limit as x approaches 0 of x squared. By direct substitution, that also equals 0. So you have 0 less than or equal to the limit as x approaches 0 of x squared cosine of 20 pi x, which is also less than or equal to 0. The only logical conclusion is that this limit itself has to equal 0. So the limit as x approaches 0 of this x squared cosine of 20 pi x is equal to 0 by the squeeze theorem or by the sandwich theorem, whichever you prefer. Let's do one more. One more, then we're done. All right, so let's take the limit as x approaches 0 of this function, x to the 4th times the cosine of 2 divided by x. So we want to find the limit as x approaches 0 of x to the 4th cosine of 2 over x. Well, when you start out, just look at the trig piece of this. Don't consider the x to the 4th just yet. Let's just deal with the cosine of 2 divided by x. So the cosine of 2 divided by x, well, okay. So what, again, is the lowest value you could hope to get from the cosine function? That's -1, right? So -1 is going to be less than or equal to the cosine of 2 over x. And then the maximum value you could get from the cosine function is +1. So this will be less than or equal to +1. Now you have this x to the 4th piece on the function, so go ahead, multiply everything by x to the 4th. You'll end up getting negative x to the 4th is less than or equal to x to the 4th times the cosine of 2 over x, which would be less than or equal to x to the 4th. Now at this point, let's go ahead and find the limit. So let's take the limit of each piece. So the limit as x approaches 0 of that negative x to the 4th is going to be less than or equal to the limit as x approaches 0 of this x to the 4th cosine of 2 divided by x, which is less than or equal to the limit as x approaches 0 of this x to the 4th. Well, let's consider the left and right side of this inequality. the limit as x approaches 0 of negative x to the fourth, we can use direct substitution. We'll end up getting 0, which is less than or equal to the limit as x approaches 0 of this middle piece, that x to the fourth cosine of 2 divided by x, which is less than or equal to the limit as x approaches 0 of x to the fourth. Once again, we can use direct substitution. You'll get that limit to be 0. So if 0 is less than or equal to the limit as x approaches 0 of x to the fourth cosine of 2 over x, and that's less than or equal to 0, the only conclusion left is the limit of this middle function has to be 0. So the limit as x approaches 0 of x to the fourth cosine of 2 over x is equal to 0. That's exactly what you'd end up getting. So the squeeze theorem, when you see it in a book and when it's first presented to you, can look very hideous and very confusing to understand. But once you understand what it's really saying, that if the middle function comes between the other two functions and the two outer functions have the exact same limit, then that means the limit of your middle function is going to have that same limit. It's going to be equal to the limit of the other two functions then. That's all that's really saying. And these damp trig functions are not the only time this occurs. That's largely where it occurs. But the other functions are not as pretty to deal with. So largely, especially in Calc 1, we just deal with damped trig functions. So that's largely what you'll see in Calc 1. As you get into other courses, you might see different varieties that employ the squeeze theorem or the sandwich theorem. So that's it for this lesson. Next lesson, we're going to go on to something called the precise definition of a limit. So I hope everybody has a great day. Take care.